Look up at the night sky tonight. Those tiny pinpricks of light you see aren't just stars. They're time machines. Every glimmer carries a story from the distant past. Some so ancient, their light began traveling before Earth even existed. But what if I told you there's something even older out there? A cosmic whisper so faint, so delicate, that it carries the very first photograph of our universe. Not a painting, not a theory, but an actual snapshot from the dawn of time itself. This is the cosmic microwave background, the afterglow of creation, and it's been hiding in plain sight all around us. Close your eyes for a moment and imagine peeling back the layers of the cosmos, traveling back nearly 14 billion years to a time before galaxies, before stars, before even atoms had fully formed. What you'd see is a universe so young, so unimaginably different, that the only way to understand it is by listening to the faint echo it left behind. That echo is still here, woven into the fabric of space, waiting to tell us its secrets. Where are you watching from tonight? Look up, that glow between the stars. That's the universe's first light, reaching out to us across eternity. And by the end of this journey, you'll never see the night sky the same way again. Now, let's step back to the moment that started it all, the Big Bang. Picture the universe not as the vast, star-filled expanse we know today, but as an unimaginably hot, dense fireball bursting into existence in a single, explosive instant. As this newborn universe expanded and cooled, it left behind a faint but unmistakable signature, the cosmic microwave background, or CMB. Think of it as the universe's baby picture, a snapshot taken when everything was just beginning to take shape. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, stumbled upon this cosmic whisper almost by accident. While working with a sensitive antenna at Bell Labs, they kept detecting a persistent, mysterious noise, a faint, uniform hum coming from every direction in the sky. At first, they blamed pigeons nesting in their equipment, even cleaning out the antenna to eliminate the interference. But the noise remained. What they discovered was the afterglow of the Big Bang itself, radiation that had been traveling through space for nearly 14 billion years, cooling as the universe expanded until it became the faint microwave signal we detect today. This discovery earned them the Nobel Prize and forever changed our understanding of the cosmos. The CMB isn't just random noise, it's the oldest light in existence, a relic from a time when the universe was a seething plasma of particles and energy. As that plasma cooled, light was finally able to travel freely, creating the glow we now see as the CMB. That's why scientists call it the afterglow of creation. It's the last, fading echo of the universe's fiery birth, still visible in every direction we look. And the next time you hear static on an old television, remember about 1% of that snow is actually the CMB, the universe's first light, reaching out to us from the very beginning of time. Now, let's journey even deeper into the past, back to a time when the universe was just a newborn, barely 380,000 years old. Imagine a cosmos still in its infancy, a place where no stars, no galaxies, not even the simplest atoms as we know them today existed yet. Instead, the universe was a swirling, opaque sea of particles, protons, electrons, and light, all trapped in a chaotic dance. At this moment, something extraordinary happened. The universe had cooled enough for electrons and protons to finally combine, forming the first neutral hydrogen atoms. Before this, light couldn't travel far without being scattered by free electrons, making the universe as foggy as a dense morning mist. But now, with atoms stable and electrons bound, photons, particles of light, were suddenly set free. For the first time, light could stream across the cosmos unimpeded, creating a glow that would one day become the cosmic microwave background. This was the universe's first clear breath, the moment it transitioned from a hot, murky plasma to a transparent expanse. The light released at that instant has been traveling ever since, stretched and cooled by the expansion of space over billions of years. Today, we detect it as the CMB, a faint microwave whisper from the dawn of time. Every direction we look, we're seeing that ancient light, a snapshot of the universe at just 380,000 years old. It's like uncovering a fossil, but instead of bones, we're studying the very first light to ever shine freely. And here's what makes it even more remarkable. The patterns in that light, tiny variations in temperature, aren't random. They're the seeds of everything we see today. Those faint fluctuations were the blueprints for galaxies, stars, and even us. The universe was laying the groundwork for its own future, and we're just now decoding its first message. But how do we capture this ancient light and read its secrets? The answer lies in the remarkable missions that have mapped the cosmic microwave background with astonishing precision. Picture a fleet of cosmic detectives, satellites like COBE, WMAP, and Planck, each designed to scan the sky and decode the faint whispers of the early universe. The journey began with COBE, the Cosmic Background Explorer, launched in 1989. For the first time, it revealed the CMB's near-perfect blackbody spectrum, confirming predictions of the Big Bang theory. But COBE's most groundbreaking discovery was spotting those tiny temperature variations, fluctuations as subtle as 1 part in 100,000. These weren't just random blips. They were the fingerprints of density, differences in the infant universe, the very seeds from which galaxies would later grow. Then came WMAP, the Wilkinson Microwave Anisotropy Probe, in 2001. With sharper vision, it refined COBE's map, measuring the CMB's fluctuations with even greater detail. WMAP's data allowed scientists to pin down the universe's age 13.8 billion years with unprecedented accuracy, while also revealing the exact mix of ordinary matter, and dark energy that shapes our cosmos. But the crown jewel of CMB mapping was the Planck satellite, launched in 2009. Planck's instruments were so sensitive they could detect temperature variations as small as 1 part in a million. Its maps are like high-resolution snapshots of the universe's infancy, uncovering subtle patterns that hint at the physics of inflation, the rapid expansion thought to have occurred just fractions of a second after the Big Bang. Together, these missions have transformed the CMB from a faint glow into a treasure trove of cosmic history. Every fluctuation, every slight variation in temperature tells a story a story of how the universe grew from a nearly uniform soup of particles into the intricate web of galaxies we see today. And as we'll soon discover, these tiny ripples hold even deeper secrets about the forces that shaped our cosmic home. Now, let's take a closer look at what these tiny temperature variations actually mean. Imagine the early universe as a vast, simmering pot of soup, almost perfectly smooth, but with the tiniest lumps and ripples swirling beneath the surface. Those minuscule differences in temperature, some as slight as a few millionths of a degree, are the cosmic equivalent of those lumps. They might seem insignificant, but they tell us something extraordinary, where the universe was just a little denser or a little emptier in its earliest moments. These fluctuations, known as anisotropies, are like cosmic breadcrumbs. Where the temperature was slightly higher, matter was packed a bit more tightly. Where it was cooler, space was a tad more spread out. Over billions of years, gravity got to work, pulling those denser regions together, while the emptier zones stretched even wider. The result, the sprawling cosmic web of galaxies and voids we see today, all traced back to those faint imprints in the CMB. But here's what's truly fascinating. These anisotropies aren't random. They follow a precise pattern, like the ripples from a pebble dropped in a pond. Scientists call this pattern acoustic oscillations, and it's essentially the echo of sound waves racing through the hot, dense plasma of the young universe. Those waves froze in place when the cosmos became transparent, leaving behind a snapshot of their rhythm in the CMB. By studying this rhythm, we can uncover the universe's ingredients, how much ordinary matter, and dark energy it contains, and even glimpse the physics of its explosive birth. So the next time you hear about the CMB's temperature variations, remember, they're not just data points. They're the universe's way of whispering its origin story, one subtle fluctuation at a time. And as we'll see next, these whispers also reveal the invisible hand of dark matter, shaping the cosmos in ways we're only beginning to understand. Now, let's follow those cosmic breadcrumbs even further, because those tiny temperature variations in the CMB didn't just hint at the universe's past. They planted the seeds for everything we see today. Picture this, in the early cosmos, where the CMB showed slightly denser patches, gravity began its slow, relentless work. Over millions, then billions of years, those overdensities regions where matter was just a fraction, more crowded, acted like cosmic magnets, pulling in gas, dust, and dark matter. At first, the process was subtle. A few extra particles here, a slightly stronger gravitational tug there. But as time stretched on, these small differences snowballed. Gas clouds collapsed under their own weight, igniting the first stars. Those stars grouped together, drawn by the same ancient overdensities, forming the earliest galaxies. And galaxies, in turn, clustered into the vast, filamentary structures we now call the cosmic web. What's astonishing is how perfectly the CMB's anisotropies map onto today's universe. Those slightly warmer spots, they're the ancestors of galaxy superclusters. The cooler patches, the sprawling cosmic voids between them. It's as if the universe left us a blueprint, and we're only now learning to read it. But here's the real kicker. Without those initial, minuscule fluctuations without the CMB's faint whispers, the cosmos might have remained a featureless sea of particles. No stars, no galaxies, no us. So the next time you gaze up at the night sky, remember, every glittering galaxy owes its existence to those delicate ripples frozen in time, 13.8 billion years ago. And as we'll soon see, dark matter played a silent but starring role in this cosmic drama. Now, let's listen closely, because the cosmic microwave background isn't just a silent snapshot. It's a recording of the universe's first symphony. These are acoustic oscillations, sound waves that rippled through the hot, dense plasma of the early cosmos like echoes in a cosmic canyon. Imagine the universe as a seething ocean of particles and light, packed so tightly that photons couldn't travel far without colliding with electrons. In this primordial soup, gravity pulled matter inward, while the intense pressure of radiation pushed it outward. This push and pull created vibrations, sound waves that traveled at nearly 2/3 the speed of light. As the universe expanded and cooled, these waves froze in place, leaving their imprint on the CMB as subtle variations in temperature. The peaks and troughs of these oscillations tell us how matter clumped together, like ripples revealing the shape of a pond's surface. Scientists call this pattern the cosmic baryon acoustic oscillations, and it's the universe's way of leaving behind a ruler, a standard measure of how structures grew over time. What's remarkable is how these ancient sound waves still guide our understanding today. The spacing between galaxy clusters, the vast voids between them, they all trace back to those primordial vibrations. It's as if the universe hummed a tune 13.8 billion years ago, and we're just now deciphering its melody. And here's the twist. Dark matter, invisible and mysterious, conducted this cosmic orchestra. While ordinary matter danced to the rhythm of sound waves, dark matter's gravity set the tempo, shaping where galaxies would eventually form. But that's a story for another moment, because next, we'll uncover how the CMB reveals dark matter's hidden fingerprints. Now, let's pull back the curtain on one of the universe's greatest mysteries, dark matter. While it remains invisible to our telescopes, its presence is written all over the cosmic microwave background. Think of the CMB as a cosmic detective, uncovering clues about this elusive substance that makes up roughly 27% of the universe. Here's how it works. In the early universe, dark matter's gravity acted like an invisible hand, tugging at the primordial plasma. Ordinary matter, the stuff we can see, was drawn into the gravitational wells created by dark matter, much like leaves gathering in the eddies of a stream. But unlike ordinary matter, dark matter didn't interact with light or radiation. It simply shaped the cosmos from the shadows, leaving its mark on the CMB's temperature patterns. Those tiny fluctuations we see in the CMB, they're not random. They reveal where dark matter's gravity caused matter to clump together, creating the seeds for future galaxies. Without dark matter's influence, the universe would look vastly different, far smoother, with fewer structures. The CMB shows us that dark matter was the unseen architect, sketching the blueprint for everything we see today. And here's something even more fascinating. By studying these imprints, Scientists can map where dark matter was concentrated in the early universe, even though we still can't see it directly. It's like finding footprints in the snow. You might not see the animal, but you know it was there. The CMB gives us a way to measure dark matter's distribution with incredible precision, helping us piece together how it shaped the cosmos over billions of years. But the story doesn't end there. Dark matter's fingerprints are just one piece of the puzzle. Next, we'll see how the CMB also holds clues to another cosmic enigma: dark energy, the force accelerating the universe's expansion. Now, let's turn our attention to another cosmic mystery: dark energy. While dark matter sculpted the universe's structure, dark energy is the force pushing it apart at an ever-increasing pace. The cosmic microwave background holds vital clues about this enigmatic energy, which makes up a staggering 68% of the universe. Here's the connection. The CMB's patterns don't just reveal the past, they also hint at the universe's future. Dark energy's influence is etched into the very geometry of space, subtly bending the paths of light that traveled for billions of years to reach us. By measuring how the CMB's light is stretched and distorted, scientists can trace how dark energy has shaped the cosmos over time. Imagine the universe as a balloon inflating faster and faster. Dark energy is the unseen hand pumping air into it, stretching space itself. The CMB acts like a snapshot of that balloon's surface, capturing the moment when its expansion began accelerating. Tiny temperature variations in the CMB correspond to regions where dark energy's push overcame gravity's pull, leaving a faint but measurable imprint. What's truly remarkable is how the CMB confirms dark energy's dominance. The way galaxies cluster, the distances between them, even the universe's overall flatness, all align with predictions based on the CMB's data. Without dark energy, the cosmos would look entirely different, its expansion slowing under gravity's grip. Instead, the CMB shows us a universe racing toward an uncertain future, driven by this invisible force. But the story doesn't stop here. The CMB's revelations about dark energy also tie into one of cosmology's most profound discoveries: the universe's flatness. Next, we'll explore how this seemingly simple geometric fact reshaped our understanding of the cosmos. Now, let's take a step back and marvel at one of the most mind-bending revelations from the cosmic microwave background: the universe's flatness. It sounds simple, but this geometric fact is anything but ordinary. Picture space as a vast sheet of paper, stretching endlessly in all directions, with no curves or bends. That's the startling reality the CMB has confirmed. Here's how we know. The CMB's temperature fluctuations act like a cosmic ruler, measuring the angles of triangles formed by the universe's structure. In a curved universe, those angles would add up to more or less than 180 degrees, like on a globe, but the CMB shows they match perfectly, just like on a flat sheet. This precision alignment means the universe, on the largest scales, is geometrically flat. Why does this matter? Flatness is a smoking gun for cosmic inflation. The theory that the universe expanded exponentially in the first fraction of a second after the Big Bang. Inflation would have stretched space so much that any initial curvature became imperceptible, like smoothing out wrinkles on a balloon as it inflates. The CMB's flatness is exactly what inflation predicts, giving the theory its strongest evidence yet. But flatness isn't just about geometry, it's tied to the universe's fate. A flat universe implies a delicate balance between matter, energy, and expansion, one where gravity's pull and dark energy's push are perfectly matched. Without this balance, the cosmos would have collapsed long ago or torn itself apart. The CMB's flatness tells us we're living in a Goldilocks universe, where everything is just right for galaxies and life to exist. And here's the twist. Flatness also hints at something even grander, the possibility that our universe is just one bubble in an infinite multiverse. But that's a story for another time. For now, let's turn to another cosmic clue hidden in the CMB, the echoes of inflation's gravitational waves, which might hold the key to the universe's very first moments. Now, let's dig deeper into one of the most compelling pieces of evidence hidden within the cosmic microwave background, the fingerprints of cosmic inflation. This theory suggests that in the tiniest fraction of a second after the Big Bang, the universe underwent an unimaginably rapid expansion, stretching space itself faster than the speed of light. And the CMB holds the clues that make this wild idea more than just speculation. Here's how it works. Inflation would have smoothed out the universe like an iron flattening wrinkles in fabric, explaining why the cosmos appears so uniform on large scales. But it also left behind tiny quantum fluctuations, minuscule ripples in space-time that got stretched across the universe as it expanded. These ripples are precisely what we see imprinted in the CMB's temperature variations, like faint echoes of the universe's explosive growth spurt. The numbers tell the story. The patterns in the CMB's fluctuations match predictions made by inflation models with stunning accuracy. The distribution of hot and cold spots, their sizes, and even their spacing align perfectly with what inflation says they should look like. It's as if the universe left us a detailed blueprint of its earliest moments, and scientists have spent decades decoding it. But inflation didn't just leave behind temperature variations. It also generated gravitational waves, ripples in the fabric of spacetime itself. While we haven't directly detected these primordial waves yet, the CMB's polarization patterns might hold their signature. Finding them would be like uncovering the final piece of the inflation puzzle, confirming that the universe really did undergo this incredible growth spurt. What's truly mind-blowing is how inflation solves multiple cosmic mysteries at once. It explains the universe's flatness, its uniformity, and even the seeds of galaxy formation, all with one elegant idea. And the CMB is our best window into that fleeting moment when the entire cosmos transformed in the blink of an eye. Speaking of transformations, let's turn our attention to another cosmic enigma, the hunt for those elusive primordial gravitational waves and what they could reveal about the universe's very first instance. Now, imagine if we could hear the universe's very first whispers, the faint tremors of spacetime itself. That's the promise of primordial gravitational waves, ripples born from the violent expansion of cosmic inflation. While we've yet to catch them directly, Scientists are hot on their trail, and the cosmic microwave background might just hold the key. Here's the exciting part. These waves would leave a unique mark on the CMB's polarization, a swirling pattern called B modes. Think of it like the universe's fingerprint pressed into light. Detecting this signature would be like finding the smoking gun for inflation, proving that space-time itself was stretched and squeezed during those first chaotic moments. The challenge: these signals are incredibly subtle, buried under other cosmic noise. Experiments like BICEP and the upcoming Simons Observatory are scanning the skies with ultra-sensitive detectors, peeling back layers of interference to spot those elusive swirls. It's a painstaking process, like listening for a single note in a symphony of static. But why does this matter? If we find B modes, it wouldn't just confirm inflation. It could reveal the energy scale at which it happened, opening a window into physics far beyond what our particle colliders can reach. We might even glimpse clues about quantum gravity, the holy grail of unifying Einstein's relativity with the quantum world. For now, the hunt continues, a testament to human curiosity and the CMB's endless surprises. And as we refine our tools and techniques, we edge closer to answering one of cosmology's biggest questions: what set the universe in motion? Up next, let's tackle another puzzle, the Hubble tension, where the CMB's story seems to clash with how we measure the universe's expansion today. Now, let's turn our attention to a cosmic puzzle that's been keeping scientists on their toes: the Hubble tension. Picture this: we have two ways to measure how fast the universe is expanding, and they're giving us different answers. It's like checking your speedometer and your GPS, only to find they disagree. One method uses the cosmic microwave background, that ancient light from the early universe, while the other relies on nearby stars and galaxies. Both approaches are rock solid in their own right, yet they don't quite match up. Here's where things get intriguing. The CMB tells us the universe is expanding at a certain rate, based on the physics of the Big Bang and the afterglow we've been studying. But when astronomers measure the expansion using nearby supernova or pulsating stars called cepheids, they get a slightly faster number. The difference might seem small, but in cosmology, even a tiny gap can point to something profound. Maybe a missing piece in our understanding of dark energy, or perhaps new physics altogether. Why does this matter? If the discrepancy is real and not just a measurement fluke, it could mean our standard model of the universe needs a tweak. Maybe dark energy isn't as constant as we thought, or there's an unknown particle influencing the cosmos. Some even speculate it could hint at extra dimensions or other exotic ideas. The Hubble tension isn't just a technical hiccup, it's a potential doorway to deeper discoveries. Right now, teams around the world are double-checking their data, refining their tools, and searching for any overlooked errors. New telescopes, like the James Webb Space Telescope, are joining the effort, offering sharper views of those local stars and galaxies. Meanwhile, theorists are brainstorming fresh ideas to explain the mismatch. It's a lively debate, and the CMB remains at the heart of it, challenging us to rethink what we know. So, what's the takeaway? The Hubble tension reminds us that the universe still holds mysteries, even in the things we think we understand best. And as we untangle this cosmic knot, we might just uncover something extraordinary. Up next, we'll explore an even wilder idea. Could the CMB's quirks be whispers from multiverse? Now, let's venture into one of the most mind-bending ideas in modern cosmology. Could the cosmic microwave background hold clues to a multiverse? Imagine our universe as just one bubble in a vast cosmic foam, with countless other bubbles floating alongside it, each with its own unique laws of physics. Some scientists believe that subtle oddities in the CMB might be the faint fingerprints of these neighboring universes brushing against our own. Take the so-called cold spot, for example, a puzzling patch in the CMB where temperatures dip lower than expected. One wild explanation: it could be the imprint of a collision with another universe during the early moments of cosmic inflation. While this idea is still speculative, it's a tantalizing possibility. If true, it would mean the CMB isn't just a snapshot of our universe's infancy, it's a window into something far grander. Then there's the larger pattern of fluctuations in the CMB. Some researchers argue that certain asymmetries or unexpected alignments in the data might hint at a multiverse's influence. Think of it like finding a strange ripple in a pond and wondering if it came from a pebble tossed by someone on the other side of a hidden divide. Of course, these theories are far from proven, and many scientists remain skeptical, urging caution before jumping to such extraordinary conclusions. But here's why the multiverse idea captivates so many. If even a sliver of evidence emerges, it would revolutionize our understanding of reality. It would mean the Big Bang wasn't a one-time event, but part of an endless cycle of universe births, each with its own story. The CMB, in this light, becomes more than a relic. It's a cosmic detective, offering hints about realms beyond our own. As we push the boundaries of cosmology, the multiverse remains a thrilling frontier. Future CMB experiments, like next-generation telescopes, could sharpen our view, searching for more clues hidden in that ancient light. Whether these anomalies point to other universes or simply new physics we've yet to grasp, one thing's certain: the CMB still has secrets to spill. Up next, we'll unravel how polarized light in the CMB reveals the universe's turbulent adolescence during the era of reionization. Now, let's turn our attention to another fascinating layer of the cosmic microwave background: its polarization. Light from the CMB isn't just a uniform glow. It carries subtle patterns of polarization, like the gentle ripples on a pond after a stone's toss. These patterns are cosmic breadcrumbs, leading us back to a pivotal chapter in the universe's history, known as the reionization era. Around 400 million years after the Big Bang, the first stars and galaxies flickered to life, flooding the cosmos with ultraviolet light. This intense radiation ripped electrons away from hydrogen atoms, reionizing the universe and ending the so-called Dark Ages. The CMB's polarized light captures echoes of this transformation. As photons from the CMB scattered off free electrons during reionization, they became polarized, leaving behind a faint but detectable signature. But that's not all. The CMB's polarization also holds clues about the universe's primordial magnetic fields. These fields, thought to have formed in the universe's earliest moments, could have influenced how matter clumped together, shaping the cosmic web we see today. By studying the twisting patterns in polarized light, scientists can probe these ancient magnetic fields, testing theories about their origin and strength. What makes this so remarkable is how polarization acts like a time capsule. It doesn't just tell us about the universe's infancy, it reveals its turbulent adolescence, a period of dramatic change when the first structures lit up the cosmos. Future observations, like those from next-generation telescopes, will sharpen our view of these polarized signals, peeling back even more layers of the universe's early story. Up next, we'll explore how the CMB carries whispers of the first stars and galaxies, imprinted in its ancient light like cosmic fingerprints. Now, let's journey even further back in time, to an era when the universe was just waking up from its dark, silent slumber. The cosmic microwave background doesn't just hold traces of the reionization era, it also carries faint echoes of the very first stars and galaxies, the pioneers of light in a once shadowy cosmos. This period, often called the cosmic dawn, marks the moment when the universe transitioned from a cold, neutral fog to a vibrant, ionized landscape. The first stars were unlike anything we see today, massive, short-lived giants, burning fiercely and dying young. Their intense ultraviolet radiation blasted through the surrounding hydrogen gas, stripping electrons from atoms and lighting up the cosmos for the first time. These cosmic trailblazers left their fingerprints in the CMB. As their light interacted with the primordial hydrogen, it created subtle ripples in the polarization patterns we observe today. Think of it like finding ancient footprints preserved in mud. The CMB's polarized light is our window into this transformative epoch. But here's what's even more fascinating. The timing and intensity of this reionization process, imprinted in the CMB, tell us how quickly those first stars and galaxies emerged. Some theories suggest they appeared in sudden bursts, while others propose a slower, more gradual awakening. By mapping the CMB's polarization in finer detail, scientists are piecing together the story of how these early structures shaped the universe we know. And there's another layer to this cosmic detective work. The CMB also hints at the nature of those first stars, how massive they were, how they clustered together, and even how they seeded the formation of later galaxies. It's like uncovering the diary of the universe's childhood, written in the language of light and shadow. Up next, we'll delve into how quantum fluctuations, tiny ripples in the fabric of space-time, were stretched by the universe's rapid expansion and frozen into the CMB, a snapshot of the universe's tiniest beginnings. Now, let's peel back another layer of this cosmic mystery. Those tiny ripples in the CMB we've been exploring, they trace back to something even more fundamental: quantum fluctuations, the universe's earliest whispers. Picture the newborn cosmos, a seething sea of energy where particles flicker in and out of existence in fractions of a second. These fleeting quantum ripples, smaller than an atom, might have vanished without a trace, if not for inflation. Inflation, that explosive expansion in the universe's first moments, stretched these microscopic quirks across the cosmos like fingerprints on a balloon blown to cosmic size. What began as subatomic shivers became vast hills and valleys in the density of matter and energy. And when the universe cooled enough for light to break free, those frozen fluctuations etched themselves into the CMB as the hot and cold spots we observe today. Here's the astonishing part. Those random quantum jitters became the blueprint for everything. The slightly denser regions pulled in more matter through gravity, eventually growing into galaxies and galaxy clusters. The emptier patches became the cosmic voids we see between them. In essence, the universe's largest structures, threads of galaxies spanning billions of light years, owe their existence to quantum randomness, magnified by inflation. Scientists measure these patterns with breathtaking precision, matching them to predictions from quantum physics. It's as if we're reading the universe's diary from its first trillionth of a second, a time so early that even the forces of nature hadn't settled into their familiar forms. The CMB doesn't just show us a baby picture of the cosmos, it reveals the quantum seeds of all we see around us. Next, we'll marvel at how the CMB's spectrum matches a near-perfect blackbody, a cosmic fingerprint so precise it leaves no room for doubt about the Big Bang. Now, let's turn our attention to something truly remarkable. The cosmic microwave background isn't just a snapshot of the early universe. It's also one of the most perfect blackbody spectra ever observed. Imagine an object that absorbs all radiation hitting it and emits energy in a perfectly predictable way, with no distortions or irregularities. That's what physicists call a blackbody, and the CMB fits this description with astonishing precision. When scientists first measured the CMB's spectrum, they found it matched the theoretical blackbody curve almost exactly. The tiny deviations are so minimal, they're barely detectable, like a painter's brushstroke on a canvas the size of the sky. This near-perfect match is a smoking gun for the Big Bang. No other theory can explain why the universe's afterglow would have such a flawless thermal signature. Think of it like this. If the universe had a different origin, say, a steady-state model where matter is continuously created, the CMB's spectrum would look messy, with bumps and dips from competing processes. But the Big Bang predicts a hot, dense beginning that cooled smoothly over time, leaving behind this pristine thermal imprint. The CMB's blackbody nature is like finding a fossil with every bone intact, confirming a story written 13.8 billion years ago. Even more impressive, this perfection wasn't guaranteed. The early universe was a chaotic place, full of particle collisions and energy shifts. Yet somehow, when photons finally broke free during recombination, they carried this beautifully uniform thermal signature across the cosmos. It's as if the universe left us a meticulously tuned radio signal, broadcasting its birth for anyone who knows how to listen. Next, we'll see how this cosmic fingerprint has silenced competing theories, leaving the Big Bang as the undisputed champion of cosmology. Now, here's where things get even more fascinating. The cosmic microwave background didn't just confirm the Big Bang, it also dismantled rival theories that once vied for dominance in cosmology. Picture this. Before the CMB's discovery, scientists debated multiple ideas about the universe's origins. Some proposed a steady-state model where the cosmos had no beginning or end, with matter continuously appearing to keep the density constant. Others suggested cyclical universes or exotic physics that defied conventional understanding, but the CMB's near-perfect blackbody spectrum and its uniform temperature variations left little room for alternatives. Take the steady-state theory, for example. If the universe had no explosive beginning, the CMB's heat signature would look entirely different, patchy, uneven, or even non-existent. Instead, the smooth, predictable glow we observe aligns perfectly with a hot, dense origin that expanded and cooled. It's like finding a single key that fits a lock perfectly while every other key bends or breaks. The CMB didn't just support the Big Bang, it made competing ideas untenable. Even more compelling, the CMB's tiny fluctuations, those faint whispers of density variations, match predictions made by Big Bang models down to the finest details. No other theory could explain why these patterns exist or how they are distributed across the sky. It's as if the universe handed us a jigsaw puzzle where only one piece fits, and the Big Bang is that piece. Over time, as telescopes like COBE and Planck mapped the CMB with ever greater precision, the evidence became overwhelming. So, what does this mean for cosmology today? The CMB didn't just elevate the Big Bang, it reshaped our entire understanding of the universe's story. By silencing rival theories, it turned a once debated idea into the cornerstone of modern astrophysics. And as we'll see next, this cosmic blueprint still holds mysteries that keep scientists digging deeper. But even as the cosmic microwave background solidified the Big Bang as our best cosmic origin story, it didn't come without its own set of puzzles. Among the CMB's near-perfect uniformity, scientists stumbled upon strange anomalies, quirks in the data that don't quite fit the expected picture. Take the so-called axis of evil, for example. This peculiar feature refers to an unexpected alignment of temperature fluctuations across vast stretches of the sky, almost as if the universe has a faint preferred direction. It's as if you rolled a pair of dice hundreds of times and kept getting eerily similar numbers statistically. It shouldn't happen. Then there's the infamous cold spot, a region in the CMB significantly cooler than its surroundings. Some theories suggest it could be a cosmic defect, a remnant of exotic physics from the early universe. Others wonder if it's a window into something even stranger, like a collision with another universe in a hypothetical multiverse. While these ideas remain speculative, they highlight how the CMB, for all its clarity, still keeps a few cards close to its chest. Even the overall distribution of fluctuations isn't perfectly random. Some large-scale patterns appear slightly more pronounced in one hemisphere than the other, defying the assumption that the universe should look the same in all directions. Could these be statistical flukes, or do they hint at deeper, undiscovered physics? What makes these anomalies so intriguing isn't just their existence, it's what they force us to confront. Either they're cosmic coincidences, waiting to be explained away with better data, or they're clues that our understanding of the universe's infancy is still incomplete. And that's the beauty of the CMB. It doesn't just answer questions. It keeps asking new ones, pushing us to rethink what we thought we knew. Up next, we'll see how the next generation of telescopes aims to tackle these mysteries head-on. Now, as we stand on the brink of new discoveries, the next chapter in our cosmic detective story is about to unfold. Scientists aren't content to let the CMB's mysteries remain unsolved. They're building tools to peer even deeper into this ancient light. Enter the Simons Observatory, a state-of-the-art facility perched high in Chile's Atacama Desert. With its array of ultra-sensitive telescopes, it's designed to map the CMB with unprecedented precision, hunting for those elusive anomalies we just discussed. Imagine upgrading from a blurry snapshot to a high-definition portrait of the universe's infancy. That's the leap this project promises, but the ambition doesn't stop there. The upcoming CMB Stage 4 experiment, or CMBS4, will take things even further. Picture a global network of telescopes working in unison to scan the sky with razor-sharp clarity. These instruments won't just measure temperature fluctuations. They'll scrutinize the CMB's polarization, the subtle twisting of light that could reveal primordial gravitational waves. If detected, these ripples in space-time would be smoking gun evidence for cosmic inflation, that explosive growth spurt the universe underwent in its first fleeting moments. What's thrilling is how these projects tackle the CMB's puzzles from multiple angles. The cold spot, the axis of evil, those puzzling hemispheric imbalances, each could finally meet its match. Maybe the anomalies are mere statistical quirks, washed away by better data, or perhaps they'll lead us to something far more profound, like cracks in our standard model of cosmology. Either way, the answers lie hidden in those faint microwave whispers, and we're building the ears to hear them clearly. And this isn't just about solving old riddles. These telescopes might uncover entirely new surprises, aspects of the early universe we haven't even thought to question yet. After all, every time humanity has built a better window onto the cosmos, we've found something unexpected. So as these next generation tools come online, one thing's certain: the CMB still has stories to tell, and we're just starting to listen. Next, we'll explore how these ancient echoes connect to the vast cosmic web, shaping our universe today. Now, let's trace the invisible threads that weave the universe together. Those faint temperature variations in the cosmic microwave background didn't just fade into silence. They became the blueprint for everything we see today. Think of the CMB as a cosmic fingerprint, its tiny density fluctuations acting like seeds. Over billions of years, gravity got to work, pulling matter toward those slightly denser patches, while leaving the emptier regions to stretch into vast voids. This slow-motion tug-of-war gave birth to the cosmic web, that sprawling network of galaxy clusters connected by wispy filaments of dark matter and gas. The CMB's fingerprints are everywhere in this structure. Those hot and cold spots you see in CMB maps, they are the ancestors of today's superclusters and empty spaces. It's as if the universe took its first uneven breath at recombination, and we're still seeing the echoes in the way galaxies line up along invisible highways. What's astonishing is how perfectly the CMB's predictions match reality. When scientists compare the slight overdensities in the ancient microwave glow to the distribution of galaxies today, the patterns align like pieces of a puzzle. The cosmic web didn't form randomly. It followed the roadmap etched into the CMB when the universe was just a newborn. Even now, as galaxies drift apart with the universe's expansion, they're still dancing to the rhythm set by those primordial whispers. And here's where it gets even more fascinating. The cosmic web isn't just a relic, it's still growing. New simulations show how dark matter continues to sculpt these filaments, funneling gas toward galaxies and feeding their growth. The CMB didn't just shape the past, it's quietly guiding the universe's evolution, even now. Up next, we'll uncover how this ancient light reveals the universe's age with astonishing precision. Now, let's turn our attention to one of the most profound revelations hidden within the cosmic microwave background, the age of our universe. Imagine holding a cosmic clock, one that's been ticking since the very first moments of existence. The CMB is that clock, and it tells us with stunning accuracy that our universe is 13.8 billion years old. How does this ancient light reveal something so precise? It all comes down to the delicate balance of ingredients in the early universe, the mix of matter, and dark energy. By measuring the subtle patterns in the CMB's temperature fluctuations, scientists can calculate how fast the universe expanded, how quickly structures formed, and ultimately, how much time has passed since the Big Bang. It's like reading the wrinkles on a cosmic face to determine its age. What's remarkable is how consistent this number is across different methods. Whether we study the CMB, the motion of galaxies, or the life cycles of ancient stars, they all point to the same answer: 13.8 billion years. This isn't just a rough estimate, it's a figure refined to within a mere 1% uncertainty. That's like knowing the age of a 100-year-old tree down to a single year. But the CMB doesn't just give us a number, it tells a story. Those faint ripples in the microwave glow capture the universe at a specific moment in its infancy, a snapshot frozen in time. By comparing that snapshot to the universe we see today, we can trace the entire cosmic timeline, from the first spark of light to the sprawling web of galaxies around us. And here's something to ponder: the precision of this measurement isn't just a scientific triumph, it's a reminder of how much we've learned about our place in time. The next time you gaze at the night sky, remember, you're looking at a universe that's been unfolding for 13.8 billion years, and the CMB is the timekeeper that made that discovery possible. Up next, we'll explore how this ancient light even holds clues about the universe's most elusive particles, neutrinos. Now, let's venture into one of the most fascinating mysteries hidden within the cosmic microwave background: the ghostly fingerprints of neutrinos. These elusive particles, nearly weightless and almost invisible, are everywhere, streaming through you right now by the billions every second. Yet, despite their abundance, they're famously difficult to detect. That's where the CMB comes in. It acts like a cosmic detective, revealing secrets about neutrinos that even the most advanced labs struggle to uncover. So how does ancient light tell us about these shadowy particles? Neutrinos were born in the fiery chaos of the early universe, and as the cosmos expanded and cooled, they left subtle imprints on the CMB. Think of it like footprints in wet cement. The lighter the step, the fainter the mark. Neutrinos, being so light and fast, barely disturbed the primordial plasma, but their presence created tiny ripples in the CMB's temperature patterns. By studying these ripples, scientists can estimate how many neutrinos existed in the early universe, and even infer their combined mass. Here's the astonishing part. The CMB reveals that neutrinos make up a significant fraction of the universe's dark or invisible matter. They may be lightweight individually, but their sheer numbers mean they've played a crucial role in shaping cosmic history. Their relentless motion smoothed out some of the early density fluctuations, subtly altering how galaxies later formed. Without neutrinos, the universe would look noticeably different, and the discoveries don't stop there. The CMB also helps pin down the types of neutrinos that exist. We know of 3 electron, muon, and tau neutrinos, but could there be more? The patterns in the CMB suggest not, tightening the constraints on exotic theories. It's like using the universe itself as a lab, testing particle physics on the grandest scale imaginable. What's truly mind-bending is that these particles, so tiny and fleeting, have left an indelible mark on the largest canvas of all, the cosmic microwave background. The next time you hear about neutrinos, remember they're not just laboratory curiosities, they're cosmic architects, and the CMB is the blueprint that reveals their handiwork. Up next, we'll investigate one of the CMB's most puzzling anomalies, the mysterious cold spot. Now, let's turn our attention to one of the most baffling quirks in the cosmic microwave background, the enigmatic cold spot. Picture this: as scientists meticulously mapped the CMB's temperature variations, they stumbled upon a region significantly colder than its surroundings, defying easy explanation. This isn't just a minor anomaly, it's a cosmic puzzle that has sparked debates and wild theories among astronomers. So what makes the cold spot so unusual? Most temperature fluctuations in the CMB are small, random ripples, but this spot is larger and colder than standard models predict. It's as if someone took a cosmic ice cube and pressed it against the fabric of the early universe. One leading idea suggests it could be a supervoid, an enormous, sparse region of space where matter is unusually scarce. As light travels through such a void, it loses energy, creating a colder patch in the CMB. But here's the catch: the size and depth of the cold spot don't quite match what we'd expect from even the largest voids we've observed. That's where things get even stranger. Some researchers propose that the cold spot might be evidence of exotic physics, perhaps a collision with another universe in the multiverse scenario, or a cosmic defect left over from the universe's birth. Imagine a flaw woven into the very fabric of spacetime, like a wrinkle in a bed sheet, distorting the light that passes through it. While these ideas sound like science fiction, they're serious hypotheses grounded in mathematical models. Yet not everyone is convinced. Skeptics argue that the cold spot could simply be a statistical fluke, a rare but natural variation in the CMB's pattern. After all, when you're studying something as vast as the universe, outliers are bound to appear, but the more we study it, the harder it becomes to dismiss. New observations and simulations keep the mystery alive, leaving scientists torn between extraordinary explanations and the possibility that we're missing something fundamental about the cosmos. What's undeniable is that the cold spot challenges our understanding. Whether it's a window into parallel universes, a relic of the Big Bang, or just an oddity of chance, it reminds us that the universe still holds secrets waiting to be uncovered. Up next, we'll explore how the CMB might one day help us test the bold predictions of string theory. pushing the boundaries of what we know about reality itself. Now, let's venture into the realm of the unimaginably small to uncover how the cosmic microwave background might hold clues about string theory, a bold idea that reimagines the very fabric of reality. String theory suggests that the universe's tiniest building blocks aren't particles, but vibrating strings, and their harmonies could dictate everything from gravity to the laws of physics. But how do we test something so abstract? That's where the CMB comes in. Think of the CMB as a cosmic fingerprint, preserving details from the universe's earliest moments. If string theory is correct, those primordial vibrations might have left faint imprints in the CMB's patterns, subtle twists in polarization, or irregularities in temperature that today's telescopes can't yet detect. Future missions, like next-generation CMB observatories, could hunt for these signatures, offering a rare glimpse into physics at energies far beyond what any particle collider could reach. One tantalizing possibility involves cosmic strings, not the same as string theory's strings, but hypothetical defects in spacetime that could have formed during the universe's birth. If these cosmic strings exist, they might have stretched and warped the early universe, leaving behind telltale kinks in the CMB's light. Spotting such patterns would be like finding cracks in a frozen lake, revealing turbulence from a time before time. Of course, string theory remains speculative, and not all physicists are convinced it's the right path. Some argue its predictions are too vague, or that alternative theories might explain the universe more simply. But the CMB offers a unique testing ground. If we ever detect its whispers aligning with string theory's math, it could revolutionize our understanding of reality, bridging the gap between the quantum world and the cosmos. What's thrilling is that we're on the cusp of new discoveries. As telescopes grow more sensitive, the CMB may yet reveal secrets hidden in its ancient light, pushing the boundaries of human knowledge. Up next, we'll reflect on how this snapshot of the infant universe transforms our place in the cosmic story, connecting the dots between the quantum and the colossal. Now, let's take a step back and marvel at what the cosmic microwave background truly represents, a window into the universe's distant past, long before galaxies or stars even existed. Imagine holding a photograph of the cosmos as it looked just 380,000 years after the Big Bang, a time when the universe was nothing more than a swirling sea of hot, dense plasma. The CMB is that photograph, frozen in time, giving us a direct glimpse into an era when the universe was in its simplest, purest form. What makes this so extraordinary is that we're not just theorizing about the early universe, we're seeing it. The light captured in the CMB has traveled across billions of years, carrying with it the imprint of a cosmos before structure, before complexity, before even the first atoms had fully formed. It's like uncovering a fossil from the dawn of time, except instead of bones, we're studying the faint afterglow of creation itself. This ancient light holds clues about how the universe evolved from a smooth, nearly uniform soup of particles into the intricate web of galaxies and voids we see today. By analyzing the CMB's subtle temperature variations, scientists can trace the seeds of cosmic structure, the tiny fluctuations that eventually grew into everything we know. It's as if we're reading the universe's baby pictures and discovering the first hints of the personality it would one day develop. But the CMB doesn't just show us the past, it helps us test our understanding of the present. The patterns we see align with predictions made by the Big Bang Theory, confirming that our models of cosmic evolution are on the right track. And yet, there are still mysteries woven into that primordial light, anomalies that don't quite fit our expectations, pushing us to ask new questions and refine our theories. What's truly humbling is realizing that when we look at the CMB, we're not just observing history, we're part of it. The same forces that shaped those early fluctuations also shaped the galaxies, stars, and planets that would one day give rise to us. In a very real sense, the CMB connects us to the universe's infancy, reminding us that we're not just bystanders in this cosmic story, but active participants, born from the same ancient light we now study. Next, we'll explore how this profound connection between the CMB and our place in the universe invites us to ponder deeper philosophical questions about existence, our role in the cosmos, and what it all means. Now, let's take a moment to reflect on what all of this means for us. The cosmic microwave background isn't just a scientific curiosity, it's a mirror held up to our own existence. When we study this ancient light, we're not just uncovering the universe's past, we're confronting profound questions about our place within it. Think about it. Every galaxy, every star, and every atom in our bodies traces its origins back to those tiny fluctuations imprinted in the CMB. In a very real sense, we are the universe becoming aware of itself. This realization invites a humbling perspective. The same forces that sculpted the cosmos over billions of years also shaped the conditions that allowed life to emerge. The CMB reminds us that we're not separate from the universe, but woven into its fabric, a fleeting yet conscious part of an unimaginably vast story. It challenges us to ask, why does the universe exist at all? And why does it seem so finely tuned to allow beings like us to ponder these very questions? Some might find this overwhelming, even unsettling, to see our lives against the backdrop of cosmic time. But there's also beauty in it. The fact that we can decode the whispers of the early universe, that we can piece together its history from faint patterns in the light, speaks to something extraordinary about human curiosity and ingenuity. The CMB is more than data. It's a testament to our relentless drive to make sense of the unknown. And yet, for all we've learned, the CMB also underscores how much remains a mystery. Those anomalies, those unanswered questions, they're reminders that the universe is far stranger and more complex than we've yet imagined. Perhaps that's the most inspiring lesson of all. The cosmos isn't just something to be understood, but something to be explored with humility and wonder. So the next time you look up at the night sky, remember, you're not just a spectator. You're part of a story that began with a flash of light, a story still unfolding, with chapters yet to be written. And in that light, we find not just answers, but new questions, new possibilities, and an endless invitation to keep looking deeper. Now, let's embark on a journey unlike any other, a voyage back in time to witness the birth of the cosmic microwave background itself. Close your eyes for a moment and picture this. You're floating in the void, not as an observer, but as part of the universe itself, hurtling backward through billions of years in the blink of an eye. Stars and galaxies blur past you, their light rewinding until they vanish into the darkness. The cosmos grows hotter, denser, until you find yourself in a searing, opaque sea of plasma. The universe as it was just 380,000 years after the Big Bang. Here, photons, particles of light, are trapped in a chaotic dance with electrons, unable to travel freely. The entire universe glows like the inside of a star, but you can't see anything. It's a blinding fog of energy. Then, in an instant, everything changes. The universe cools just enough for atoms to form, releasing those trapped photons in a flash. That flash is the cosmic microwave background, and you're witnessing its very first moment, the dawn of transparency. Now, imagine riding one of those newly freed photons as it begins its 13.8 billion year journey across the expanding cosmos. At first, it's energetic, vibrant, but over eons, the stretching of space itself cools it into the faint microwave glow we detect today. Along the way, it passes through the seeds of galaxies, the birth of stars, the vast cosmic web, all while carrying the imprint of the universe's infancy. This isn't just a thought experiment, it's the real story of the light that fills our skies. Every time we map the CMB, we're not just collecting data, we're replaying this ancient journey, tracing the universe's first breath. And the most astonishing part, you're here now, piecing together that story. The same light that once blazed through the early cosmos now whispers its secrets to us, connecting you directly to the moment everything began. So the next time you hear about the cosmic microwave background, remember, you're not just learning about the past, you're touching it, and in that connection, the universe becomes not just a distant mystery, but a story you're part of, one that's still being written. As we bring our journey to a close, let's take a moment to reflect on what the cosmic microwave background truly represents. It's more than just ancient light. It's a cosmic Rosetta Stone, a key that unlocks the secrets of the universe's infancy. Every subtle fluctuation in its glow, every whisper of polarization, tells a story of how our cosmos evolved from a searing plasma to the vast, structured expanse we see today. Think of it this way. When you look up at the night sky, you're not just seeing stars, you're glimpsing the aftermath of that primordial flash, the echoes of a universe taking its first breath. The CMB connects us directly to that moment, bridging 13.8 billion years of cosmic history. It's a reminder that we're not just observers of the universe, we're part of its ongoing story. So the next time you step outside under a clear night sky, let your eyes linger a little longer. Imagine the invisible glow of the cosmic microwave background, still bathing everything around you, carrying the imprint of creation itself. Let that thought fill you with wonder, because understanding the CMB isn't just about science, it's about seeing the universe with fresh eyes, alive to its mysteries and possibilities. If this journey through time and space has sparked your curiosity, don't stop here. Hit that subscribe button and ring the notification bell so you never miss an adventure into the cosmos. Share your thoughts in the comments below. What part of the CMB's story amazed you the most? And as always, keep looking up. The universe has so much more to reveal. you.